Recall from yesterday that the triple integral of a function f of x, y, and z dv was defined as the limit as n approaches infinity of the Riemann sum from k equals 1 to n of f of x sub k star, y sub k star, z sub k star, and then delta v sub k. Okay, so now the idea is, if we're going to try to figure out how else we can integrate these things, we did study in Chapter 11 three different types of three-dimensional coordinate systems. Rectangular we've already been working with. We also dealt with cylindrical and spherical. So let's take the cylindrical approach first. So let's say you have some solid up here. I know that's a very two-dimensional drawing, but imagine that it's got depth and all that good stuff, okay? And then within this solid, we have a little wedge, which is going to correspond to a few different angles. So this angle will be theta 1. Well, yeah, because in the xy plane, that's where theta is, right? Theta 2 will be this larger one. And now, let's go ahead and map one of these little wedges upward. So this inner curve is going to be R1 of theta. This outer curve is going to be R2 of theta. And now this is going to map up and create a little three-dimensional wedge. With now, let's get another color in here. So now this little wedge is bounded above and below by two functions. The bottom function here will be z1. And the upper function here will be z2. Can you guys kind of visualize the little wedge? I mean, honestly, for winging this picture without having tried drawing it for the first year, it's not too bad. Usually I rehearse drawing that because it's not...
No, yours is fine.
Where's the original one?
The original one? Doesn't have colors and such, but it's pretty similar. Anyway. So this is the setup in cylindrical, all right? The nice thing is that the volume of these little wedges is just going to be the area of the base times the height. And instead of doing a long process and spending all this time deriving it, we've already done that. From 14.3, we know what the area of the base is. Remember when we did those little, what do we call them, polar rectangles, right? we know that the area of the base was essentially r sub k star delta r sub k theta sub k. The height, if we're going from z1 to z2, then that's going to be just delta z sub k. So now, an alternate version of the triple integral would be to take the limit as n goes to infinity of the Riemann sum from k equals 1 to n, and now we evaluate the function not in terms of x, y, and z, but in terms of r sub k theta, theta sub k, or I'm sorry, r sub k star, theta sub k star, and you remember in cylindrical, z doesn't go anywhere, it's still going to be there. And now, this delta v sub k that we were wondering about, very similar to what we did in 2 dimensions when we did double integrals, that goes down here.
I don't know what's happening.
It'll come out something great.
R sub k star, delta r sub k, theta sub k, delta z sub k. And here's the final formula.
Why do you have to know the previous one? Why does that matter?
Why does it matter? Because you should know where these little...
Wait, just like we should.
I just thought the star was always just like the original word. Because then you rewrite it as
Oh, wow.
R
Star
theta.
is like random.
Is it?
It should be delta. Yeah, it's the change in theta. Yeah. That would have made a big difference.
Huge difference if you ask me.
Huge difference.
Yeah.
Okay, thank you. So now when you set this up, then you're just going to have a plain old function in terms of r, theta, and z.
Wait, see exactly why do you need the star surface? It's just that.
This, because these are just arbitrary points within one of the little wedges. What we're doing here when we do this process is evaluating how we actually find the volume of one of these little boxes. And that's how we got this formula. And then by doing the Riemann sum, this is like with the r sub k stars, those become variables because those are arbitrary. Does that make sense? So this becomes just an r. And then this delta r sub k, delta theta sub k, delta z sub k, I'm going to write it in a different order, but that becomes dz, dr, d theta. So in cylindrical, appropriate limits is what I meant to write here, sorry. This is what you would do to evaluate the triple integral. That just means, I mean, if we actually wanted to write it in, it'd be, let's see, z would be a function in terms of r and theta, right? So it'd be like z1.
But it's the same as just being like over.
Absolutely, yeah.
Okay.
And then this we called, what was r? R1, R2, theta 1, theta 2, you know what I mean?
Yeah.
Wait, hold on.
Okay. Are there any questions on where this formula is coming from? Roma's a magician. You guys do need to know what this notation means. I'm going to tell you that right now. I'm not going to ask you to derive all these triple and double integrals, but if I were to say, what does this mean, you should be able to tell me, oh, well, this represents the radius, or this represents the change in theta, and so on and so forth.
Wait, so
Wait,
we
but I
have to
don't
know
even
what
know
the
what that
variable
means.
stands for?
Yeah.
Oh.
I mean, that's easy, but like... sorting
Like, I'm not going to ask you to rederive how we found the polar area, if that's what you're wondering. Okay. But you should know, like, for instance, back up here, what does this represent?
Change in volume.
Which, true, but it, in the context of what we're doing here, it actually represents the volume of one of these little arbitrary boxes. Okay, so you need to know that. And then you need to know that this represents the output of the function. In triple, in double it'd be a height, but in triple it's not really anything that we can conceptualize. But anyway. We've already done problems like this. That's the good news. Okay, so to determine the limits, identify upper surface, which we'll call z equals g2 of r theta, lower surface, which will be z equals g1 of r theta, and certainly you can convert right away now. And then 2, make a 2D sketch of projection onto the xy plane. And this will help you determine the limits or the bounds for r and theta. Okay, so let's try an example. So let's say we want to evaluate triple integral where, let's see, g lies within x squared plus y squared equals 1, below z equals 4, and above z equals 1 minus x squared minus y squared. Now, before we go ahead and set everything up, what are we actually finding here? We're just finding a volume. Why? It's just dV, right? There's no function in here. So, as far as the bounds, let's sketch what we got. I'm going to start with the surface of z equals 4, 1 minus x squared minus y squared. So 1 minus x squared minus y squared was a paraboloid, right? X squared plus y squared equals 1 is actually convenient because it's the cylinder that wraps around. And then here's z equals 4. So basically we have a cylinder that's getting cut off at z equals 4. And then within the cylinder we have this little bump that we want to remove, essentially. So we're finding the volume between this shape and then within the cylinder below z equals 4. So the bounds would be, I know you guys can do this. Let's go dz, dy, dx. Or if you want to go to polar or cylindrical, we can do that right away. Can we? R dz, dr, d theta. Don't forget the extra r. That's pretty much what we should emphasize today with cylindrical. Z is going to be a function in terms of r's and thetas, right? Well, what's the lower bound for z? 0 or 1 minus x squared minus y squared, which is really 1 minus r squared, and then z equals 4. R, what circle is this? So from 0 to 1, and then theta goes all the way around, right? So 0 to 2 pi. See, this isn't bad. So 0 to 2 pi 0 to 1, we get RZ from Z equals 1 minus R squared to Z equals 4 dr d theta. Yep.
Really quick. Could you explain how you got that 4 and 1 minus R squared?
Sure.
I know you probably did already, but I was drawing and stuff.
This is the one class you could admit you were drawing stuff.
The lower surface that's bounding the solid is this paraboloid. So that's where I got 1 minus R squared. Just plugged in the polar equation for it. And then the upper surface is Z equals 4. Okay, so where were we? 0 to 2 pi, 0 to 1. Plug in Z equals 4, Z equals 1 minus R squared. You're going to get 4R, subtract R times 1 minus R squared, dr d theta. Let's clean it up a little bit. So that's 4R minus R plus R cubed, dr d theta. Integrate with respect to R. That's 3R. I don't know if we can do that. So then 3R becomes 3 halves R squared. R cubed becomes, from R equals 0 to R equals 1. Plug in 1, you get 3 halves plus 1/4, which is 6/4 plus 1/4, so 7/4. 0 won't do anything. So then this is 7/4 theta, from theta equals 0 to 2 pi. Final answer is 7 pi over 2. One more thing, since I'm not going to finish. We'll finish this tomorrow. How about you guys get some homework questions ready so that tomorrow we can go over more stuff, all right? And we'll do a discussion on Thursday.
So tomorrow, 14/7.
Tomorrow I'm not going to, no.
He's finished.
We're going to finish 14.6. I'm going to go over some homework. And then Thursday I'll do a discussion day. Converting from rectangular to cylindrical. Because I want to give you this example, which, I mean, we'll at least talk about setting it up. If I give you a triple integral, you should be able to have the recognition within yourselves to say, I don't want to integrate this. So the idea is, could I do this in cylindrical? Okay. Let's see. We'll worry about the double on the outside in a minute. This represents Z, right? What is this going to be if I convert to cylindrical? R. 2 is good. What's x squared plus y squared? dz dy dx becomes r dz dr d theta. And now these outer bounds tell us the region R, right? Can we sketch from the bounds?
Half circle?
Half circle. Actually, it's
That's
a full circle.
Alright.
We got the lower and the upper. Negative 2 to 2 means we're going all the way around, right? So what's the bounds going to become for R and for theta? Bless you. See how easy that is? This is fun stuff. Here's the answer. You guys can do it at home.
Why?
Along with our homework.
See you guys tomorrow.
Really simple.
Why does it start at 0? That's a good question.